Everyone, good morning. Can you hear me? Thank you all for coming, and welcome to PyData. My name is Eric Keenan. I'm going to be one of the volunteers in this session. My goal here is just to help things go on smoothly. So just so you know, these talks are 30 minutes, and we'll have 5 minutes for question, and then the plan is to have 10 minutes for you all to go wherever you're headed next. So this first talk, we have Krishi Sharma, who will be giving us a talk on some of the machine learning tools that she's working. So thank you very much.
Hi, everyone. I'm super stoked to talk to you about Flower. But before we go into what Flower is and what federated learning is, I wanted to talk about data privacy, since federated learning was built to address concerns around data privacy. I learned what data privacy means for a company back when I worked at Capital One in 2019 as an analyst. One day in July, I was going into work, perfectly normal day, until I got up to the 11th floor and I saw a bunch of teams scurrying around. There was one team that was huddled up around a whiteboard. Everybody looked super tense, and I thought, man, I'm glad I'm not them. They look like they're missing a deadline. But when I got to my desk and opened my Slack, I received a message from a coworker that said, "What just happened?" Exclamation point, question mark, exclamation point. And anyone who has gotten a question with that much punctuation knows that there's a problem. It turns out that Capital One was the victim of a data breach that affected 106 million customers, 66,000 bank accounts. Somebody at AWS, a former employee, hacked into Capital One's data warehouse on AWS and downloaded all that data, put it onto Git, while live tweeting the whole process just in case we wanted evidence. This severely impacted Capital One's reputation for the time when that happened, because Capital One believes in innovating and using new tools such as the cloud in order to solve problems within a highly regulated industry like finance, where data privacy is legally regulated and of true concern. Besides the reputational damage, the stock slipped that morning 5.4%. They had to pay $80 million to the federal bank regulator because of poor cybersecurity practices. And they had to pay out $190 million to all the customers that were impacted by the data breach. So why should we innovate, particularly in these red tape industries? Why take the risk of working with such sensitive data? I mean, the truth is, I think that there's so much to gain from building these technologies. I think that it's brave, and we need to continue working on using AI and machine learning to solve some of these problems within finance and healthcare. And we can build our best tools if only we know how to use the data behind it. So how do we use private data and sensitive data to build machine learning models when there's so much red tape around them? To really understand that, I want to talk about the challenges that classical machine learning presents to sensitive data. In classical machine learning, we typically have a central server that ends up storing all of the data required for the model and trains the model. It gets the data from different data stores or devices. The red dot is data. That data is copied from the different devices, let's say your smartphone or tablet, and sent to the central server, where it is then used to train a model. So now all of your private data is in the cloud somewhere with everybody else's data being used to train a model. The benefit is the automation that we get with the AI product. But the drawbacks are data privacy, and security. What if a data breach happens to that central server? We've lost control of our private data because it's left our device. But also, this isn't highly scalable, because what if we need more compute than the single machine can give us? So another approach is to look at distributed machine learning. With distributed machine learning, you typically have your central server and all of the different devices where you're getting the data from. The data is again sent to the central server, but this time, instead of the central server being used to do the compute and train the model, the central server sends that data into different nodes. So there are subsets of the data across different compute instances, and each compute instance trains a model, which is then aggregated into a single final model. This is really awesome because it solves that scalability issue. We can leverage horizontal scaling, and we can add more and more nodes and get more and more compute. So this can make it more efficient and potentially less costly. But we're still sending our sensitive data to a central server, and there's still more risk for server-side attack or security around each of the individual compute instances. So it increases our exposure. In all of these scenarios, we are sending our data to the model. But what if we could send the model to our data? That's what federated learning does. So with federated learning, you have the same setup. You have a central server and all of the different devices that have this personal data. But rather than sending your personal data to the central server, each of the devices will locally train a model using just the data that is on that device. So the server never touches the data. Instead, the devices send the server model weights after it's finished training of the local model. And the server aggregates all of those model weights to create a new set of parameters, which it then sends back down to the clients or the devices. So rather than the server containing all of our data, it actually now just contains the only things that it needs for the model, which is the model weights and metrics. And that creates a final model. When I first learned this, I was like, why are we not using federated learning all the time? As a consumer, this makes me feel a little bit better about the fact that my data isn't just everywhere. But the truth is that there are drawbacks to federated learning that make it difficult to implement. The first one being compute. So with federated learning, the training isn't happening on a compute instance that you own and you can control, but is rather using the compute on the devices where the data lies. And so if there isn't enough compute, then that means that you may not be able to train the model, or it may be very slow. The second one is networking. With traditional machine learning and distributed machine learning, typically you just need to send the data to the server. That's one call. But with federated learning, there's a constant communication between the server and the different devices. So if you have slow networking or unreliable networking, then it can pose some issues. The best places to use it is therefore in these red-taped industries, which is exactly what my team did. We ended up having to work on a healthcare project where we were tasked with building a model that would predict the likelihood of breast cancer within the next 5 years. When we were tasked with this, we had to figure out what tools to use. And we ended up evaluating 3 main choices. The first choice was PySift. PySift was originally designed for working with PyTorch Lightning, but now handles TensorFlow as well. But we found that the documentation was a little difficult for us to navigate, and it was undergoing major changes. The next one we evaluated was TensorFlow federated, but the major drawback was that it only worked with TensorFlow, and we were considering using PyTorch Lightning for training. That's when we came across a third option, which was a relatively new package that was quickly gaining steam within the federated learning community, which is called Flower. Flower was framework agnostic, so it would work with TensorFlow or PyTorch Lightning or any other framework that we needed. And it also had really clean and thorough documentation. It was built around research purposes by researchers in Germany. So we felt like it fit our needs for the exploratory phase of our project. And it also allowed us to quickly interchange between different features around the server configuration. So we chose Flower. The way Flower works under the hood is we have a Flower server and then Flower clients, which are the different devices where the data is held. And each of those clients train a model. The central server has to grab parameters from one of the clients. So it'll initialize by taking it from the first client it connects to. And then it'll send down the parameters to all of the clients once they've connected in order to instantiate the first round of training. Each of the devices will train a model, and then they'll do the evaluation. You can also do evaluation on the server itself rather than on the client side, but you would need data on the server. After the evaluation rounds are done, they send back parameters to the central server, which then applies an averaging function in order to create the final model. You can define how many rounds you want to train it, and the more rounds that you train it, typically it'll get better until a certain point. So if you wanted to do another round, you would train the model and run the evaluation, and then the devices would send back the parameters to the Flower server. Flower allows you to quickly aggregate your metrics, so you can figure out different formulas and define that on the server. You can also aggregate the model weights with using different averaging functions. And you can compress the model weights to allow for a faster communication between the server and the devices. So the best way to understand Flower, in my opinion, is through a demo. So I put together a demo with using a containerized application and an already built model to demonstrate exactly what Flower can do with few lines of code. So just give me a second while I pull up the repo. And okay. Oh wait. Okay, so in this repo, we have existing code that you don't necessarily need to worry about. We have the model and the data sets for each of the clients and code around how each client is configured. So this is all using exactly what they have in their documentation, but just fit to the sample data set that I have. And these should be pretty recognizable features for people who do machine learning, but it just has a fit and evaluate function. And besides that, if we wanted to start, we would start with configuring our server. And the way to do that with Flower is after you import it, just want to make sure. You use the server submodule, and you start the server by defining a server address. So, oh, yes, thank you so much. That's also a great idea. How do I dim the lights? Is that better? Oh. I'm okay with off if everyone can see it. Yeah, I can definitely. Is that better? Okay. Thanks, everyone. I appreciate it. Okay. So we're going to just define our server on our local host, or 000, and port 8080. And then we have to give it a config. So the config has basically two settings, a timeout, which I'm not going to use, but the more important one is actually the number of rounds. So as we discussed, you can send the model weights from the server to the client. That's one round. So I'm going to say let's do it for 3 rounds, just so we can see better results. And also a strategy. So the strategy is actually the averaging function that the server will use in order to aggregate the model weights after each round is complete before sending the new weights back down to all of the clients. So the common one is just federated averaging, which is a simple averaging formula, but they do have more complex ones, and they do allow you to define your own. And you can tell it how many clients to expect. I have to say strategy. Sorry, and you can tell it how many clients to apply the fit to. So how many you want to use for evaluation and fit. I'm just going to do fit the same as the number of available clients, which is 3. And then you can bring up your server. Since I'm using Docker Compose, I just am bringing up the server using the service, which I've defined for Flower. This repo is on GitHub, and I'll share the link after in case you want to actually understand under the hood what's going on there. But once we start the server, we see that it knows that it has to run for 3 rounds, and that it's waiting for initial parameters from one random client. So now we have to kind of make sure, create our first client and make sure that it has connected to the server. So to do that, we just have to use the Flower server and then use the client function. And we're going to start a NumPy client, but you can also just start a normal client. I just selected NumPy because that was the example that my team has used. You need to give it the server address. So because...
Font sizes again?
Thank you. Is that better?
Thank you.
Yeah. So I'm using a Docker container, and so I'm just going to tell this server address as the Docker container name. But otherwise, if you have networking set up, then you can kind of put it to wherever the address is. 8080. And then I also need to give it a client. So that means that I have to create an instance of the client that I have defined already, which is our MNIST client. And it inherits from this base class that gives you all of these different properties. And all it does is it allows the server to get weights if the server needs a set of weights, which ours does currently. And it fits the model and does the evaluation on the client side. So for our client, we can say we need the MNIST client. And the one thing that I need to provide the MNIST client is some device name or ID, since I'm going to be spinning up 3 of these. So I'm going to say that our device ID is just going to be whatever I put into the terminal. Hold on. Oh, hold on. Yeah, we do need to give it a device ID, but I have a client config, so I'm going to give it there. Client config. The client config has it has different configurations that you would need for the client. So the server address is here. It takes in the device ID, which we're going to give it, and then different hyperparameters for your clients. You can have different hyperparameters for each of the models for our 3 devices, but we're just going to stick with the same ones. But know that you can actually change up the hyperparameters as long as the model architecture stays the same. So with this, we should have a configured client when we run our script to start up our first client. So we're going to give it the script and then device ID 1. So this is our first device, and if the code works, we should see that it is connected to the server and it is fetching its parameters and then sending it to the Flower server. So the Flower server now has a set of parameters, and we just need to give it 2 more clients, since we've said that we want 3 clients. So to do this, I'm going to then connect a second client and call it device 2. And then give it a third client. And after this third client, we should see that the 3 rounds are kicking off and that we're getting a fit and evaluate 3 times before the server closes. So we can see that the training has run for each of the clients. So each of the clients will have this kind of output. And our server will automatically shut down. It'll give us the losses over the 3 rounds. So you can see that the loss is minimizing every time. And if we actually give it a way to aggregate the metrics, it will also give us a metrics distribution, which I will show you on a different branch because I don't have the code for it off the top of my head. But this is essentially all you need to get started with a server and a client. So to see how it would work with a metrics aggregation function, I will show you the piece of code that you would need. This is more just neater code to create the server, but we can start with a weighted average function and pass that in to our server or our strategy that we initialized for the server. And this evaluate metrics aggregation function will then provide us the weighted average. So then this metrics distributed will also be populated, and you'll be able to see how the metrics have improved over each round. So if we wanted to start our server again and connect our 3 clients. So it's fetching the data every time because I'm using a dummy data set from scikit-learn or something, I think. But this time, after the 3rd client has connected, we will see the metrics improve, hopefully. Yeah, so this time we're logging accuracy, but you can see that the accuracy of the model has improved over each round as well. So you can play with different configurations like the number of rounds or even what aggregation function you want to use for your metrics when the server has collected all of them and wants to kind of output the final metrics distribution. And then you can also play with the hyperparameters on the client side if you wanted to further improve the model. The other thing you could do, which is not related to Flower, but is related to just machine learning in general, is you can obviously add more data and add more devices and connect your server to multiple devices. Flower makes it really easy to scale for thousands and thousands of clients. It has a few server-side configurations that you can find in their documentation in order to kind of quickly connect to thousands of clients. So that is the demo on Flower, and if you can turn the lights back on while I get the presentation back up. Okay. So overall, you can see that Flower helps us with the scalability issue, and it also helps us with data privacy since the server never touches the user's data. And now you don't really have to worry about security around the server when it comes to data breaches because there is no data on your server. So overall, we can kind of feel more confident as consumers, I think, when understanding that there are options out there in the future for how to protect some of our sensitive data while getting the benefits of AI. If you want to use the code that we just walked through, then feel free to copy down the tiny URL. It contains the link to the GitHub repo that has the containerized application. And this is my contact, and my company's name is Kung Fu AI. If you want to learn anything more, feel free to talk to me. And yeah, that's it. I'm open for questions. Yes.
Yeah, maybe I missed it in your demo, but is Flower also updating the models on the client side after every iteration of training?
Yeah, it'll send forward like a new set of weights to each of the clients, and the clients will take those set of weights. That's part of like that Flower abstract base class, and it'll like then kick off a new round of training with those weights.
Gotcha.
Yeah.
You don't do it. It's not like asynchronous. Like the model weights could be different on each client.
Yeah, the model weights are different on each client because it's fitting to the data like that's locally on that device. But
when you after you're done with the round and you send all the model weights back, do you send them back all at the same time, or?
Yeah, so with the way that Flower is like natively set up, from our team's experience, you send them. It kind of kicks off each round at the same time, which can cause an issue if like one client is a little bit slower or has like a lot more data. But my team actually figured out a way to kind of make it asynchronous. So they're publishing a paper. So I'll make sure to put it in the GitHub repo and the README if you're interested.
Thank you.
Any other questions?
Yes. Well, you mentioned some slowdowns and some potential issues due to networking. Do you have any sort of benchmarks that could show like how different model training is in terms of time if you were doing it the old-fashioned way when you have all the data without having to send it over the network, and when you're training it using Flower? Like how different on the scale, especially like with the larger models, language models or whatever. How different the training time?
I actually don't have metrics. So the question was like if there are metrics to compare the networking speed between maybe using a classical machine learning approach and federated learning. I don't have metrics since we were not able to use classical machine learning. We were bound to federated learning because we were working with healthcare data for our project. But I'd be interested to know if there are experiences out there with that.
Thank you.
Okay, I think that, oh yeah.
Do the initial model weights come from the server or from the clients?
Oh, okay. Yeah, so the initial model weights come from the very first client that connects to the server. Alternatively, you can kind of initialize the server with model weights, but I believe you have to have like data that you've trained on that server. So if you don't have any data, then typically like it'll default to waiting for that first client and grabbing its parameters.
I see.
Yeah.
So depending on the client, you can get different initial parameters?
Yeah. Yeah, exactly. It's just waiting on a random client. Like that's what the logs say. So you can control that a bit, but the default is just, it'll take it from any client. And basically those initial parameters are one client's specific parameters to that data. So.
Thank you. I'm wondering if you could talk a little bit about like how these tools could be useful, like maybe in contexts where like data privacy isn't as valuable. Like I think like certainly that's an emerging trend, but there's also like other sides to this that are valuable. I'm just curious to hear if you have anything to say on that.
Yeah, so the question was, are there use cases for federated learning outside of scenarios where data privacy is the concern? I believe that it's being used a lot with like IoT where it can, but I think that, you know, because you have to like set up the clients and you have to do the networking, it's not really the default. I kind of was expecting, like I was kind of hoping like self-driving cars would use it because there's like a lot of data on there, but because you have to be with Wi-Fi, it's kind of hard. So I haven't really heard of actually too many use cases besides Siri. Siri is trained using federated learning, and they were able to kind of improve its ability to pick up on your voice by using your data and only training the model locally. But I think other than that, I actually don't know of any other like cases outside of the highly regulated industries.
Yeah, that's kind of.
Okay, well, if there are no other questions, thank you everyone for attending my talk, and I hope that you enjoy the rest of PyData Seattle.